So I've entitled my presentation Pushing the Limits of Instrumentation Using CMOS MEMS. CMOS MEMS is really the core of our research, so I apologize for not bringing in the nano stuff that you maybe would like to hear, but your nano stuff will have to be connected to the macroscopic world using some other dimension in between, so we may be of help anyway. And it's a fascinating research field anyway, as I hope to prove to you. So I have the following outline. After a very brief introduction into the structure of my group, I will then address three topics: magnetic field sensors, mechanical microsystems, and neural probes, which represent three areas of the research in my group. And that will also be, of course, a good illustration of the diversity that you have in MEMS. MEMS is interdisciplinary by nature, just as nanoscience is interdisciplinary. MEMS has that interdisciplinary in its name by electromechanical, but nowadays, of course, it goes far beyond, and the connection with the life sciences in the last part is going to be one aspect that that it has become quite precious to me, because we have acquired this very substantial 30 million euro fund for a center of brain interfaces that will run at the University of Freiburg for the next 5 years, and hopefully renewable for another period of 5 years. So I have been at IMTech indeed since 15 years, and I was the fourth professor of now over 20, so I have experienced the growth that you have undergone in the last few years. And so from virtually zero, we came up to a staff of about 300 and 600 students at bachelor and master level, plus about 180 PhD students are populating our buildings, new buildings also, well, no longer so new buildings, but still quite attractive, honestly. Yeah. And so my group relies heavily on PhD research by roughly 10 PhD students. It's structured by some postdoc and group leaders, and then I have some staff helping with the fabrication and instrumentation and secretarial tasks. And as I said, this is just one group, and then of course you have master and bachelor students working on their projects in my group, which double the group size roughly. And this is just one group among 20 at the institute. And my research is really focusing on silicon MEMS, silicon components, and what you can do with it to address challenges in instrumentation, both for industrial as life science applications, as Michael mentioned. So one part of projects deals with magnetic sensors based on silicon technologies. Then I have been quite active over the last 10 years in mechanical sensors, microsensors. You see here an example of a structure of a tactile finger that has the size of about 6 by 6 by 6 millimeters, which is now implemented in an instrument by Zeiss Instrumentation, the instrumentation company or branch of Zeiss. Big machine with a lot of control and optics and electronics, and then there is this tiny sensor in the core, the central part that makes the measurement possible. It's an electromechanical sensor based on a silicon chip, and Zeiss, of course, has quite a substantial margin when you compare the size of or the price of this little sensor as compared to that whole system. So MEMS shows itself to be an enabling technology in this particular case. Now, third, intracortical probes will be the last part of my presentation. And then we also do materials characterization, mechanical properties, thermal properties, using test methodologies that we have to invent ourselves, because these are non-standard methods. You have these tiny materials, and you cannot just take a machine off the shelf of some company to make a measurement. You have to invent the machine. And this goes in my group very often through the development of microstructures, test structures that are specifically designed to reveal the property that we would like to have. Just like Michael invents these test structures for revealing the properties of the bonding processes underneath the bonding pads. And then the final research group is dealing with microenergy harvesting, mostly from vibrational energy sources, using electret and magnetic effects, well, electrostatic and magnetic effects, and so The common denominator of this is that in virtually all our developments there will be some silicon, and in many instances there will be CMOS silicon, that is silicon produced by commercial CMOS processes, the ASIC foundries out there like X-FAB or Micronas or others. And then we do the enhancement of these silicon wafers by micromachining techniques, by structuring them, or by adding other materials like polymers or metals and interfacing them by assembly techniques. And so of course I'm quite happy actually to say that we have two companies, and this number increases so fast that even in this slide it's already out-fashioned. So from last week, Michael Meyer, the CEO, told me that there are 500 now. Yeah, the 300 were probably true 1.5 years ago. Yeah, and this is the later last year. So, and then we have this little company, Atlas Neuroengineering, who is starting to commercialize these intracortical neural probes with currently 3 persons. Yeah, but it may grow. It's a totally different market from what Sensorion does, a niche market, but well, that's also a business model. So why to do CMOS MEMS? Well, first of all, so what is CMOS MEMS? It's about microelectromechanical systems, so these complex systems that exploit electrical, mechanical, thermal, and other effects, optical effects. But we are doing that compatibly with CMOS technology. That is, we take wafers that can be fabricated at commercial ASIC foundries, and for this reason we have to exploit the effects that these materials offer to us. Yeah? Thermal, mechanical, optical, and whatever effects. And then a big important part of our development is, of course, then use that understanding of these effects, these materials, to design structures that reveal what we want to measure, a magnetic field, yeah, cleaned of mechanical effects or of thermal effects, for instance. And then, of course, doing CMOS technology, you can integrate these sensors with circuitry, with smartness. You can do smart systems. And the technology transfer problem is already partially solved by the approach, because we are using processes that are commercial. So we can right after the end of a PhD thesis, tell the company how to produce the sensor, because the sensor has already been developed for their technology, for instance. And so that is quite handy and has enabled at least the foundation of these 2 spin-off companies that I've mentioned before. Is that something exotic? Not at all. CMOS MEMS are done now also by industry. Robert Bosch is a big player, which sells about $500 million in product worth of MEMS products, accelerometers, inertial sensors in general, pressure sensors, magnetic sensors, flow sensors. Micronas is a mid-sized company specializing on the measurement of magnetic fields, but they are also venturing in other directions, although these are not yet large product areas. They have been ASIC foundry for many years, serving the customer products, audio, video products. And about 5 years ago, there was a big crisis because all the fabrication capabilities, the development moved to Asia. And so they were in search of a model that could keep them in Germany. And their then small business of magnetic sensors was able to grow into what is now the dominant part of the company, and very successful. They serve the automotive industry, the commercial goods companies. And then Sensorion, that has already been mentioned before, is a still smaller company. Well, it's growing so fast that soon it will be mid-sized, specializing on humidity, flow, and temperature measurements. And all these applications are done using CMOS chips that integrate circuitry. Now, when you talk about microsensors, you have this, what I call the intimacy challenge of microsensing. You have an environment that you would like to sense. You have a sensitive device, and of course that sensitive device needs to be encapsulated somehow, connected or separated from the outside world. So there are several levels of doing that. The easiest one is that the environment is really an external world that sends a pervasive signal through the sensor, like a magnetic field will just penetrate any non-magnetic sensor, and then you can measure it en passant, like a voyeur, and not being noticed by the external situation. And here the encapsulation is really a simple thing. All you have to ensure is that you do not distort the magnetic field. So you can use a wide variety of materials. In other cases, when sensing mechanical signals like the force or torque or contact, tactile information, you need the direct contact with the environment. And so the encapsulation must be designed to fulfill another purpose, namely to focus, to direct, to eliminate undesired signals. So the engineering will then also include the encapsulation much more than in the case of this first scenario. And then finally, you can also have the case when the environment becomes extremely close to the sensor, when you have this invasive unity of sensor and environment, and that's especially the case if you're making measurements in the brain. Then you cannot separate your device from the brain because you would like to access information provided by the brain. Neuronal signals that are generated, single unit activity of neurons that needs to be measured in ultimately intimate contact. And so here the encapsulation challenge and the stability challenges are huge, and we're working on those. So let me now come to the first topic, which is maybe more from the electrical engineering. In the second part, I will then go back more to the mechanical engineering part, and in the final we'll deal with some bio applications. So I would like to first talk about Hall sensors and what we can learn from close studies to make them better. Planar Hall sensors are well known. These are some flat sheets of material, a semiconductor, ideally with 4 contacts, and current is sent across the device, and then under the influence of a perpendicular magnetic field, a perpendicular voltage is measured, and that voltage grows linearly with the magnetic field. So there is an output voltage that has a term that grows linearly with the magnetic field, and of course linearly with the drive signal, and then a sensitivity parameter. That would be a perfect world if that was all. In reality, you also have an offset, because these contacts are not exactly placed opposite each other. 10 nanometer of offset, of geometrical offset already generates a significant offset signal here in the electrical domain. The sensitivity now over the years we have learned how to understand it. It's basically given by the Hall mobility and a geometry factor. That's all there is. You only need to calculate a geometry factor, and you need to know the transport property. And so when you optimize such a device, of course you would like to increase the sensitivity as much as possible, and that is pick the right material, the low doped silicon, and then optimize the geometry until that factor becomes maximum. So that would be the engineering approach to make the best possible sensor. And then of course you have this remaining problem of the offset, which is done, well, by best possible design within the limits of a technology, and then additional compensation techniques that removes the offset. Unfortunately, in the case of planar Hall sensors, this is possible. Now, of course, you say, okay, how will it be possible to optimize the geometry factor? Geometry is a wide design space, so how do we do the best sensor? Well, it turns out that the question is simple to answer. All sensors of a geometry that is simply connected with 4 contacts at the periphery cannot exceed in sensitivity a certain level. So that is an absolute top level that is built into the galvanoelectric transport mechanism operative here, and whatever shape you take, wherever you place your contacts, if you have this kind of symmetric device, you are not going to go above this number of 0.47 for the geometric factor. That is actually the same as the geometric factor, sensitivity divided by Hall mobility. And so that's quite interesting. And well, if one might be surprised at the first, after some reflection, of course, one sees the differential equation governing this transport, and then one sees that every device can be mapped onto any other device by a conformal mapping. So they're electrically, physically identical, and all you do is just distorting the shape of the device without even changing its electrical properties. So that is something which we had to learn, and then of course then you can optimize the device by designing the best sized contacts, and then you obtain something like 6.8 volt, 68 millivolt output signal per volt drive signal per Tesla magnetic field. And the Hall signal that you get out now, for instance, for an Earth magnetic field would be something like 2 microvolts, which is just handleable by integrated circuitry. So you can, with this result, you can be sure to be able to measure the Earth magnetic field and possibly also the direction of the Earth magnetic field with a silicon-based sensor. So that's comforting when you think about low-cost magnetometers. Now, what about sensors that do not measure the magnetic field in this out-of-plane direction? That's only one component of a three-dimensional vector. So in order to measure two other components with the same chip, you would have to integrate two other differently designed structures able to measure an in-plane magnetic field component. And that the logical idea would be to turn around the sensor into the vertical direction, but then it would have contacts at the bottom somewhere buried in the silicon. So what can you do with that? Well, you have to pull out the contacts to the surface, and that's exactly what it looks like. You have this Hall plate, which is now rather oblong, and it has contacts at its periphery. Now there are 5 of those, but once we connect the outer ones together, then again we have 4 effective contacts through which to send current and extract current, and then 2 more to measure a magnetic signal. And now that sensor is going to be sensitive to magnetic field in the plane of the sensor, but it looks quite different from the planar Hall device. So one asks the question, can it be a good sensor or not? And well, due to its unfavorable geometry, its sensitivity has decreased to 2% per Tesla, 20 millivolt per volt per Tesla, and the offset that was very small in the planar Hall device now has grown out of proportion to huge signals that are much larger than the microvolts of signal that you can extract. So we were faced with that problem by Micronas to analyze these devices and make them better. So they could also think of measuring Earth magnetic fields in the plane of the sensor. And so, of course, the student tests and applies voltages here and there and tries to extract as much understanding as possible. And so what he found very early already was that when you operate the device, let's say like here, with a current injected in the center and then extracted at the 2 peripheral contacts, he could measure a voltage, that would be the Hall voltage, but in the absence of a magnetic field, this is the offset voltage. Well, that offset voltage is significant. It's in the range of millivolt, very large. And you can reverse the current. The voltage is still huge, of the same size. So covering all magnetic signals. If now we invert the contacts and make what were current driving contacts now voltage measuring contacts, and what was voltage measuring contacts now current driving contacts, these modes look quite different. The current flows through the device in a complicated manner, and again you obtain huge offset voltages. Now the lucky part of that is that if you do an average of those 4 signals, they average out pretty much. At least on that millivolt scale, you think that the offset voltage has been removed. So doing 4 measurements can remove this undesired offset and get you just the pure magnetic signal. But if you go closer, you will see that there is still a significant fraction of a millivolt remaining here. Yeah? And so the goal of doing a better Hall sensor would be to remove that altogether. And then you would have this pure signal. So we analyzed the device and said, okay, well, it's a simple device. It's 4 resistors in series. Yeah? There are some inner resistors between these 2 pairs of contacts and then outer resistors between these 2 pairs of contacts. They're slightly different because the electrical surrounding, the N well through which this current goes is terminated here, whereas the inner resistors don't see that termination so easily. So such a device, well, it is closed here on top with these shunt resistors, and then you have your contacts. Actually, there are 4 contacts that you effectively use. And so, well, it took us quite a while to find out how easy actually it is. It's nothing else than a Wheatstone bridge. And that Wheatstone bridge can now be deformed from the original device here into this classical Wheatstone bridge connection. And now you have your 4 resistors, these 4 segments, some shunt resistors. And what now is important is that these resistors, these semiconductor resistors, are non-linear resistors. The voltages that are applied between the contacts influence the depth of the N well of the depletion layer here, and that makes the resistance change with the voltages applied. And then you have a non-linear device, and that's what makes the device complicated, and that's the fundamental reason for these strongly non-linear offset signals. So that was the first part of the understanding, and now a Wheatstone bridge of this type, well, we know how to analyze that. We can do all kinds of expansions according to disturbing signals, and then identify the reasons. And the reason is really that this Wheatstone bridge is not symmetrical. Yeah? There are shunt resistances only on one part, and there are outer resistors that are different from the inner resistors. So no wonder that under circular rotation sending driving signals in, this device will not be compensated perfectly. So the logical consequence is, let's make it symmetrical, really symmetrical. And that we condensed into a patent, and then, well, now the patent has been filed, and so I can also show the results. We rely on 3 contact devices, of which we take 4, and that we connect together in this way that, well, one output is always the input of the next one. Yeah? And so we have 4 central contacts. And now if you see this as a 4 contact element, you can apply voltages wherever you want. Yeah? It's just a permutation of always the same element. So this is intrinsically symmetrical. Yeah? And the measurements show that indeed the signals, the offset signals are much more controlled. So these curved signals without the lines are those of this non-symmetrical device. And now here we have the symmetrized device. Yeah? So what you remark is that the nonlinear content is gone away. Yeah? That is really eliminated. We still have some linear signals, yeah? Similarly to the previous case, but this is much more balanced. Yeah? And the linear influence still comes from some resistive mismatch of the device, yeah? Which is hard to avoid. Yeah? But the outcome is that when you do now the averaging, yeah, this operates at a much better level, and the residual offset that you obtain then is about a factor of 10 lower than you had in the previous case. So your resolution is increasing by a factor of 10. Let's go to the next topic, mechanical microsensors. Yeah? So here the encapsulation has become the environment. Yeah? If we take the situation of a silicon chip with its interconnection to some lead frame, yeah, through some or some interconnection layer with some solder balls, then of course this is going to be the region of highest stresses and where failure will happen. So it is important now to know what mechanical, electromechanical and thermomechanical effects are arising here. And so, of course, two are temperature and mechanical stress that are acting on the sensitive device that will cause delamination, fracture, you name it. And so the idea is to implement micro-mechanical sensors right here at the interface where the action happens. Yeah? So all in the spirit of Michael's work here, concentrating on bond wires, but here now applied maybe to a larger scope of encapsulated chips in general. So the example that I'm taking here is also the most spectacular that I can present. It's a chip that we developed in collaboration with Intel in Oregon, and it contains hundreds of locations of solder ball connections to the opposite interconnection layer. And so below that chip, of course, there would be in a real chip all the central processing unit or whatever graphical unit, whatever you need. Yeah? This is just the interconnection layer that you see. But of course, these solder balls in such number are centers of possible failure, and the chips get thinner and thinner. And so Intel wanted to know what the stresses are under these balls. And so we designed this large chip, which is of a realistic size. Yeah? Central CPUs are centimeters by centimeters large. And it contains hundreds, over 1,000 sensors, stress sensors, temperature sensors underneath that surface. And to bring that out a little bit better, I have highlighted it. So that's the design of the chip. With its sensors, you have here an interfacial structure, some I2C bus, and multiplexer that can address any sensor here. And then you have sensors that are very small structures that are arrays of microsensors sitting underneath these individual balls, able to measure the shear stress exerted by the ball in a thermomechanical environment, or the vertical stress or the in-plane shear stresses under these structures. So, and so there are sensors in different symmetrical locations, so we can really test very precisely what happens under different of these balls. And then we have other structures that measure in between that can give us some 2D profiles of the mechanical stresses on the packaging overall. Now, just to give you an impression of what these sensors can do, here is a little demo of a situation where a similar chip has been bonded to a PCB, and then an epoxy cylinder has been grown or solidified on top with a little force interaction element here, through which we can act in the horizontal directions, in the vertical directions, and which we can also rotate. And so this structure, you will see, can be used to control some application in the background. So the signals that are coming from the sensor are recognized as forces from certain directions. So now in the horizontal directions, now in an oblique direction, and this information is translated into a particular motion of that virtual element. So quite intuitively, pushing, pulling, and then maybe also rotation. So that's also quite visible. So using this chip, we can measure at least 4 degrees of freedom of mechanical influence and translate it into a control signal. In the case of the packaging, this would be the detection of the influences, the local forces, the stresses acting on the surface of the silicon chip in a similar way. So the effects that we are using here is piezoresistance. So any resistor with 4 contacts, again, can be used as such a strain gauge. We call it piezoresistor in the MEMS technology. They are made of silicon, usually embedded in silicon chips. And of course, you have some nominal resistance R0 that is then changed by the mechanical stress by some delta R, and that involves some piezoresistive coefficients and then the levels of mechanical stress to which the device is going to be sensitive. So there's the resistivity, the geometry, and then the material constant and the external situation to be measured. So overall, the signal that comes out of these sensors is quite substantial. So let's take 10 to the 8 Pascal, 100 megapascal. That's not an unrealistic level of stress. This through the piezoresistive coefficient of the order of 10 to the minus 9 per Pascal will produce a 10% change of resistance change. And that's a significant element. So you can resolve in the lower megapascal easily. Now, these resistors we connect again into Wheatstone bridges, because then you have certain effects compensated, like the temperature dependence of the resistive effects, or we make, again, Hall sensor-like structures with 4 contacts that are also good stress sensors, but those would additionally be also magnetic field sensors, of course. So we usually go now for this kind of design of an open loop with a central free area of resistors. And then you can measure mechanical stress like the shear stress or a difference of normal stresses in the plane of the chip. Here are some examples of structures. These are field effect transistors. The size from here to here is about 30 micrometers. So the sensitive area is about 20 micrometers in size. We have 4 contacts placed at these points. We have an additional contact here, which is the contact to a gate, because these structures are field effect transistors. So the inversion layer underneath the silicon oxide going from a source to a drain, these layers, these inversion layers, are the conductors that are exposed to the mechanical stress that will be deflected under mechanical stress, so that a voltage is measured perpendicular to the current direction. And again, you see here structures that look like Wheatstone bridges, and others that are filled like these Hall sensors. Both are good stress sensors. And you see them in 2 orientations, distinguished by a 45-degree rotation. Those we design as NMOS structures. They are very sensitive to the shear stress, whereas these PMOS devices here, in view of the piezoresistive coefficient of p-doped silicon or P carriers, will be sensitive to the difference of normal stresses. Then in addition, we have invented some new structures, because these structures, well, the effects that are used here have been traditionally used in other configurations. We introduced this field effect transistor concept, which is very handy because you have this additional gate to switch them on and off. So for making arrays, that's a wonderful thing. You only have to switch on and off the gate, whereas the drive currents and the sense instrumentation can remain online. Previously, this was done using diffused resistors, which needed a much larger signal or circuit overhead. And so we're using here now the same material for making possible measurements that were not done before. For instance, the vertical shear stress, out of plane stress is here the topic, and this structure can measure a shear stress that operates vertically. And for that reason, we again, like with the Hall sensor, we turned the horizontal sensors in the vertical direction and let a current flow in the vertical direction, and then have some additional contacts on the surface. And without going into the details of the functioning, this makes it possible to measure other components of the 6-dimensional or 9-dimensional stress tensor. And then these vertical resistance structures enable us to make measurements of the out-of-plane normal stress. So integrated into chips, these structures can now be used to make this kind of measurements as in the packaging testing or in this joystick application. They're distributed here, according to application in certain strategic locations, 3 different types of stress sensors, again integrated with the smartness of this smart system. And in this case, this is a chip that is used for orthodontic applications. You see here an artificial jaw. This is not a patient. It's plastic, with plastic teeth, but it serves to test some new orthodontic wire loop ideas that in this case are designed to pull this teeth into the hole horizontally without its flipping over into the hole. It should be exposed to a horizontal force and a moment, so that it will translate as a rigid body into that hole. And such a loop can do that. And for the orthodontist researcher to be sure that he proposes a new treatment to the practitioners out there that really works, he has to measure these things. And so thanks to these chips, that we can integrate into these brackets individually, and powering these chips through these lines, we can now measure the force and torque applied to each individual tooth. Yeah? And so our partner at the University of Ulm can now put that into a publication and say, now do this, do my loop. Yeah? And then you will be successful with your clients, and you'll spare half a year, yeah, in treatment. So this would be the full instrumented Typodont, where you see that it's not a real patient. Yeah? All the teeth have been instrumented, and so the full mechanical system can be tested at once. Yeah? That was not possible so far, and MEMS makes it possible. Now, since I suspect there are maybe also some mechanical engineers, here's another application where it's about pressure sensing, yeah? Using again, these piezoresistive gauges. So the structure we're using is a silicon glass bonded bilayer with a thin silicon layer that has been microstructured by deep reactive ion etching and contains a piezoresistive gauge here in the center. So the structure would work like this. If a pressure is applied to this overall cube, the glass with its low elastic modulus will contract, and because it represents the major part of the mass, it will just pull the silicon along. Yeah? Well, there is a little bit of curvature, as you see also, but as an effect of this contraction of the overall cube, you see that here a strongly anisotropic stress appears, which is shown here. And then you have only to place one of those piezoresistive sensors in here. And the structure, being a simple mechanical structure, can be used for very high pressure, 600 bar. Yeah? That is quite substantial. And these are pressures that are technically relevant in engines, for instance, where the explosion of the motor has to be controlled. And so this would be a way to access these pressures. Yeah? So that's a structure as it looks. And again, you see that you can easily obtain 0.3 megapascal here for an applied hydrostatic pressure of 1 megapascal. And such pressures are easily measured using these piezoresistive elements. So let me continue. So of course, encapsulation is then an interesting aspect. How do encapsulants react to such high pressures? But this has been worked on by the PhD student successfully, who has identified one silicone encapsulant that is able to repeatedly withstand these large pressures. Yeah, so let's come to the final part, the neural probes, which is well, what we started about 5 years ago and now has been amplified into this big program at University of Freiburg with many other co-PIs. And so here we are talking about really making a connection to the brain. So what is the medical vision behind this Brain Links, Brain Tools project? Well, there are some ailments that are going to hit one or the other of us at our age, hopefully only then and hopefully never, but there is a chance. And some of them are listed here. So paralysis, yeah? Paralyzed patients could greatly benefit from a higher mobility if brain signals could be interpreted and turned into motion by some helping device. Yeah? Stroke rehabilitation could benefit if brain signals could be used to stimulate other brain regions to train the person to overcome the ailment of some lesioned region. Also, wouldn't it be wonderful to effectively reduce some symptoms of Parkinson's disease in a more moderate way than is done nowadays? Now we have these deep brain probes that go deeply into the brain. These are strong wires that will be used to dispense currents that calm the electrical circuitry of the brain, so to speak, and reduce the tremor. But this is kind of a crude way, and so the idea is really to make this more subtle and attack the precise region, the precise group of neurons that might create this oscillatory loop. And then finally, also epilepsy patient could benefit from having their seizure detected before it starts, and then the brain to be calmed before it goes into this uncontrolled firing state. So to just show you an example of what is possible, what has been possible already 2 years ago, you can look at this image here now. Should this move? Yes, it does move. So what you should see here is that this person has electrodes attached to the side of its eyes. So the neural signals governing the motion of the eyes are used to direct this robot. And once the robot is in the desired position, it takes over the job of grabbing the object. It would be way too hard for the person to think now, grab the object and do this complicated tactile motion that we do every day with our hands to direct the computer to do the robot to do that reliably. The robot can do it himself, thanks to the achievements of computer science and robotics. But the intention of the thought of what is to be achieved can be given by the patient. So what if we were able to extract much more fine signals from the brain, yeah? Not just these very superficial signals from the surface, for instance, using epicortical grid arrays or intracortical probes that get really into intimate contact with the neurons. There are, of course, systems that already do that, deep brain probes, intercortical and epicortical grid arrays, both for recording and stimulation, but the current methods are relatively crude, and we're confident that using MEMS technology and computer science know-how, we can go far beyond the current state. In particular, you can connect these structures into full systems, implanted systems that can then either be used as autonomous systems that can fulfill their job of recognizing an epilepsy seizure and calming it down, or calming down the tremor of a Parkinson's disease person, or you could use it through some exchange of data and communication device to direct some external prosthetic device, for instance. Yeah? So previously, people have done similar things using wires. You see here various arrangements of wires. It's kind of scary to look at them, but they have been used with some success, undoubtedly. Nevertheless, people in the MEMS community have started already quite some years ago to produce more controlled structures, like these still pretty scary nail beds, yeah, with electrodes sitting at their tips, shaped in various ways that can be implanted on the surface of the cortex to reach down into signals. And last year there have been some very spectacular reports on the media of a person with such an array to be able, a paralyzed person, to be able to shake the hand of her partner in life through a robotic hand, solely governed by these neural signals. A very emotional video, I must say. Yeah. And University of Michigan with Ken Wise have worked on a different approach, making much more slender needles, very fine structures with fine cables that achieve the same goal. Yeah. Now, in our group, we have worked on probes that contain much more channels to access the brain. Yeah. Because when you, let me just show this here, when you sticks one of those invasive probes into the brain. Yeah? This is a process that is invasive, no doubt. And if you do that, at least you would like to be able to extract as much information as possible. Yeah? Not to have to fill the brain with such invasive structures, but to have one that is able to extract wherever there is activity, or to fire back at every desired location. Yeah? Instead of having to move around this probe in the vertical direction in search of areas of activity, you just put it into place, and then you search electronically where the activity is happening, and then you select your channels to interact with the brain structure. And so we call that electronic depth control. And you can see this here on this structure. So here would be one of those probes with a slender shaft. And then in more resolution, you see that there are electrodes that are then generating the interface to the brain, or representing the interface to the brain, platinum electrodes. And underneath, you have microelectronic circuitry able to address these individual electrodes. Yeah? So using such structures, neuroscientists have indeed mapped the activity of a cross-section of the brain here in the case of a mouse, and they were able to identify that, well, this is the most interesting location for recording at that moment of time, and then maybe down here there are some single unit activity as well that might be interesting to follow. And these probes are fabricated using MEMS technology. So we take the silicon wafer as it comes back from the CMOS foundry. We add some passivation and metal lines and cover everything with a tight passivation. And then we have these metal electrodes, these platinum electrodes exposed to the electrophysiological medium that is the brain. And then the silicon is deep reactive ion etched vertically to a thickness of about a depth of 100 micrometers. It is then ground back from the rear until the desired thickness of only 50 micrometers of these probes is reached. And now the probe has its in-plane shape, its slender shape through these etchings here, and then it has its thickness through that back grinding. And then finally you can assemble the structures with some highly flexible cables through some flip chip bonding technologies. These cables are also fabricated in my lab based on polyimide, or Kapton as it is called here in the United States, and then connected to whatever connector the neuroscientist desires for his own setup to be able to translate the signals into some recording or some display. And then, of course, these structures can also be built into 3D structures. You have now a whole array of such needles, each one very slender, each one carrying hundreds of these contacts. And so you can really do an extremely dense interaction with the brain. And I will not go into the details of this technology here, but rather come to an end. And so there are further developments, of course, in this area. Well, one is that 5 years of European projects have been sufficient to create the basis for another spin-off that now commercializes these EDC probes with an interconnection box, and then some connectors again to the design or wish of the clients, and then some insertion devices that they can use to really target the position in the brain where they can do their experiment. And we're currently working on flexible probes that are less stiff than the silicon probes, on the next level electronic depth control probes, putting more intelligence into those, some two-sided and deep brain probes, and then also probes integrated with active optical elements for a new area of neuroscience, which is called optogenetics, where neuronal activity is triggered or hindered using optical input. These are genetically modified neuronal cells that will then be made reactive to optical information. Yeah, with this I would like to thank you for your attention. Maybe keep just 2 messages. CMOS microsystems are diverse and powerful in many ways. They're also used, and successfully used for packaging testing, and Michael continues to prove that with his own valuable work. And neural probe technology is really experiencing a renaissance now. The state of the art that I showed you was between 15 and 20 years old. It died down for a number of years, but now it's really having a renaissance, and well, the NIH and other government agencies here in North America are also heavily pushing that topic, and we're happy to benefit of the funding of the German Science Foundation in this area, and hopefully we'll be able to benefit in our not so near future, myself as an aging person. So, and for sure these approaches will help us to continue in this scenario of more than Moore that will provide the microelectronic industry with some juice for a number of years. So, thank you very much.
The resistance in your Hall sensors, when you do the averaging, do you find that your average offset is decreased?
Yes.
Compared to the case where you had the nonlinear resistance. I think you had a graph
yes.
that showed that. Like, what was the extent of the reduction in offset from the averaging?
So, yeah. So if you take the planar sensors, you had these individual mode offsets with a size of, let's say, 10 millivolt. yeah, 10 millivolt. And after the averaging, you're down to roughly a tenth of a millivolt, yeah, 100 microvolt, which is still substantial when you compare that with the signal of 2 microvolt that you could possibly measure. Yeah? I mean, the microelectronic circuitry is definitely able to amplify a signal of 2 micron and keep the noise low enough to get some meaningful signal out of that, yeah? some measure of the B field. So by switching now to these fully symmetric devices, we are reducing the offset into the order of 10 microvolts, and by combining several of those structures into even more compensated structures, we're now down to below the 1 microvolt level. So it's a significant reduction. Well, so of course that is an interface to the brain. Yeah, it's short-lived. At the current stage, it lives for several months. Yeah? So neuroscientists are able to make measurements, well, not just of the acute type, but what they call subchronic measurements. Yeah? And these probes survive for several months. And one reason is that you can really place them into the brain, and not have to move them anymore. Yeah? So what neuroscientists did so far was they lost their signal. Yeah, due to brain motion. There is micromotion of the brain that will shift the probe ever so slightly, and you lose your signal from your single recording location, and then you have to mechanically move again. Yeah? That mechanical motion, that searching motion, is extremely adverse to the stability, because the brain then really feels this foreign body, and the foreign body reactions will be amplified. Yeah? So leaving the structures in place, without having to touch them anymore, is certainly one first solution to make them more longer lived. But of course, they're still stiff in a very soft environment. So ideally, we would like to have structures that are as soft as the brain, with elastic moduli of a few megapascal, that have as much information interfaces as the CMOS probes have. We're not there yet. You can thin down these structures, even removing all the silicon. It's still going to be a relatively stiff structure. So the challenge will be to maybe go into polymer technologies, and maybe in some future we'll have sufficiently miniaturized switches, efficient switches in polymer technologies that will make the same kind of things possible in a really flexible probe. So that's one thing I could imagine. Then there is, of course, magnetic resonance imaging, which is a totally different thing, where micro MRI is now currently able to produce signals with resolutions at the neuronal level, but only very locally. Well, the field is very rich, it's dynamic, and people are putting in enormous amounts of ideas that come out. So of course you never know the future, but when I see the effort that goes into it now, into the development, this is much more than has been done in previous years.
And so, I'm quite excited by that level of development. It seems to me, though, that we need an order of magnitude increase in the level of funding for that research, because this is nice, it's elegant, it's much better than what we had before, but we're still talking electrons to things that talk vesicles. And in readout, it's not so bad. But in terms of stimulation, it's more primitive.
Stimulation is also okay. You can purvey these structures with iridium oxide metallization. You can add P-dot, and then you have an interface that can also be used for stimulation, and we're doing that. So it's really a bidirectional interface. Definitely.
I think I don't mean to. I'll stop any moment now. But I think the magnetic sensors are quite tantalizing in that we've got a non-invasive readout. That's quite exciting. I'm not sure if we'll ever get the same sensitivity with a Hall sensor that we had with squids.
Well, sure.
It's tantalizing.
Yes.
There may be a common ground apart from going to optogenetics?
So I really, I'm convinced that non-invasive methods will be preferable over these invasive methods. Yeah? So they are nurturing neuroscience, yeah? The understanding of the fundamental principles. I'm not sure if I would like to have one of those devices implanted into my brain, although my condition may be bad enough one day to still, push my trade-off into that direction. But that's hard to say. Non-invasive methods would definitely be preferable, and but there are some physical limits. Yeah, but the creativity is incredible. Yeah, they are starting to do micro MRI now in Earth magnetic fields with micrometer resolution. It takes still hours to take these measurements, something that was inconceivable 10 years ago. Yeah, just because somebody invented hyperpolarization, transferring spin from one system to another. Yeah? And so these are ideas that come from fundamental science, that come into this engineering field, go into this more fundamental science, but in a totally different field, neuroscience. And so the interdisciplinarity of our endeavors, I think, is a wonderful chance to progress.
I agree. Thank you.
So it's 100 electrodes along the shaft, 2 rows of 94. Yeah, so actually, so let me take out this again. So you have these little dots. There are 94 of them along the shaft in two rows. Yeah? So each of these dots are a location where the signal from a neuron could be picked up if there was a neuron nearby. Yeah? The distance between these recording sites is 40 micrometer, which is just matched to the average distance of neurons in the brain. So underneath these locations is just a switch that enables them to be switched on or off. So there is no amplification at the present level here, yeah, which is okay because people were able to extract neural signals from the brain without in situ amplification for many years. Yeah, the signals are 100 microvolts or between 10 and 100 microvolts. That's good enough to be measured outside, but of course, in a system, now where should I go? Backward. In a system like these, yeah, especially the autonomous system, yeah, you need the energy from in situ, you need the data processing in situ, you need much more intelligence locally, and that has to be taken over by some microelectronic chips that do the things you're mentioning, amplifying signals, identifying spikes, discarding non-interesting information, continuing to process that piece of retained interesting information into whatever action is necessary to counteract something. Yeah? And so neuroscience nowadays is also in learning, is also to learn how to extract the valuable information, how to identify what the brain really speaks, what we need to keep, and then how to do something meaningful with it, to back act on the brain.
The last question, what's the idea of what's the advantage of having the switch underneath the channel rather than integrated with the chip itself?
Yeah, so you see, no, I have to move forward. So the traditional electrodes had something like 8 or maybe 16 such electrodes along the shaft. Each electrode has one line running to the base of the shaft, where it can be connected to external instrumentation. Now, 16 lines integrated on such a slender shaft is already filling the shaft pretty much. So if you want to have 64 or 128 or 512, what do? You have no space, so you're limited. You cannot integrate so many lines along the shaft. So our approach was to say, okay, we can waste a number of 5 lines to control a digital switch system, to feed in some control signals, and then we can address any desired position along the shaft. And as a matter of fact, we can now address any configuration of 8 different electrodes along the shaft. So measuring with 4 locations here in the front and then 2 here and 2 here, that would be possible. Yeah? After having scanned along the shaft systematically to listen where the interesting action is, then we can say, okay, let's settle down here and here and here, and now let's listen to what the brain has to tell us. Yeah? So that is the idea of these switches.
Okay, so one last question.
Yeah, he has been waiting.
Yeah, so it seems like a lot of the material properties that are the basis of the sensors are things that the CMOS foundry want to suppress to improve their electronics. And from node to node, or from process to process, foundry to foundry, how do you, how could you import a design from one that worked in one process into another one?
Mm-hmm.
None of these material properties are really in the foundry design kits.
Well, so one thing is that CMOS processes, at least out there in the industry, are amazingly similar. So taking over one design from one design kit into another design kit of another foundry is not such a big problem. Then, of course, you might have some changes. But if it's a comparable CMOS technology, you will also have an N-well. The N-well is an N-well, and if it's now doped with 2 times 10 to the 16 per cubic centimeter here and 5 times 10 to the 16 there, this is not going to make the world change dramatically from the application point of view. But of course, it's good to know these properties, and CMOS technology is much about having reliably and repeatably the same properties, at least within the same technology. So these diffusions vary by a few percent, usually in sheet resistance. At least if you look at the properties globally over the wafer, if you look closely within a circuitry, it can be much better. So
does that apply for the poly as well and the thermocouples?
Thermocouples I haven't talked about, but obviously you're interested in that. So if you take gate polysilicon in many foundries, we made measurements back then for Austria Microsysteme, for Microelectronic Marin, for Atmel in southern France. The gate poly was always maximally doped, and so the Seebeck coefficient was always around 100 microvolts per Kelvin. And then, of course, you have these lower doped resistive poly materials that then may have several hundreds, and then you have differences among the processes, because one may offer you a high resistive poly and another one may not.
Okay, thank you very much.
Mm-hmm.